Okay, thanks everybody. Let's start with round two of this session, and we'll have Tom present again, and that's going to be on story.
Yeah, thank you, Tom. This is a description of a new NASA initiative called the Space Weather Centers of Excellence. Um, about a year ago, they awarded 3 awards to 3 centers of excellence in space weather, and we were lucky enough to be selected as one of them. It's a large team. These are consortia of research teams. So the one that we proposed and won here at CU is called the Space Weather Operational Readiness Development, or SWORD Center. It's an acronym that Dan Berger came up with. It's irresistible. And the SWORD Center involves both CU, both the Space Weather Trek organization that I lead at CU, along with LASP that Dan leads. But we have a large contingent at the University of Michigan. We have participation from NCAR, UCAR, Nick Petitella, for instance, is a co-I. And then we have researchers at the University of Iowa and the University of Alaska Fairbanks. And then finally, Marty Malinczak, when we proposed and won, was at NASA. Marty has now since retired from NASA, and he's at the Space Environment Technologies, a private company doing space weather research and consulting. So Marty's still on the team, but he's now part of SET. And Marty, of course, is was the PI of the SABRE instrument that we just heard about from Ricardo. So it's good to have him on board. So as you can see, it's a large team. I'll go quickly through what we're planning to do in the SWORD Center of Excellence Award. It's a 5-year award. We're sort of 2/3 of the way through the first year. So we're really still in the spin-up phase. So this is more of what we plan to do than report than what we have accomplished so far. Anyway, a little bit of motivation. As Sue mentioned, space traffic in low Earth orbit is rapidly increasing. There's plans for several mega constellations. There's an ever-growing debris population. And this is really kind of the hockey stick plot for space weather, if you will. This is showing the number of launches of spacecraft into low Earth orbit over the history of the space program, really. And you can see that there's this really dramatic increase in the last few years, primarily at this point due to Starlink and SpaceX's efforts to put a constellation up there. But there's going to be more efforts like Starlink's coming. And so this plot's just going to get more scary. This is a plot of the objects that are then tracked in LEO, not only in LEO, but passing through LEO. So highly elliptical orbit satellites go outside of LEO, but then they come dipping back down. And you can see that this is another scary plot. These jumps back in the earlier periods before the Starlink and constellation launches are due to collisions of things in LEO, creating large debris clouds. And so their collisions were creating jumps before, but now we're witnessing this very rapid exponential increase in launches and objects, operational objects in the space. Okay, so now we're tracking over 21,500 objects greater than about 10 centimeters in LEO, and that's growing every day. As a result, space traffic coordination is increasingly stressed. The 18th Space Defense Squadron of the Space Force is who currently issues all the collision warnings to various operators in LEO. Recently, they were issuing something like 5,000 collision warnings per day to operators in LEO. Now, not all of those are critical. In fact, the large majority of them are, quickly analyzed and ignored by the operators. But increasingly, LEO satellite operators are having to spend time and money analyzing and finding that some of these are critical, and they will require maneuvers to avoid collisions with either debris or other satellites. And what's relevant to all of us here is that space weather-driven variations in the thermospheric density, as Sue was telling us, are the largest source of uncertainty as to where things are or are going to be in low Earth orbit. So it's critical that we get better space weather modeling for LEO spacecraft operations in particular. And it's also worth pointing out that we haven't had a geomagnetic superstorm. This is in my quantification denoted by a DST value for the Earth's magnetic field disturbance of less than -500 nanotesla. since 1989. The storm we had in May earlier this year reached a DST of minus 400. So it was the biggest one we'd seen in 20 years. But we know they can get much, much larger. In fact, as Sue was pointing out, we haven't heard of any major effects of the May storm on LEO operations. There was a lot of, people working 24/7 and sitting on the edge of their chairs, but there were no real major effects. But it's worth pointing out that that particular storm is nowhere near as strong as the 89 storm or the 1921 storm, which was even much, much larger than 1989. And of course, there was nothing in orbit in 1921, so we have nothing to compare to in that particular storm. So that's the motivation. We've got to get better at forecasting what I call orbital space weather, in particular low Earth orbital space weather. And the SWORD Center is focused on doing just that. So how are we going to do that? Well, what we propose to do is take the two operational models I talked about in my talk, running at SWPC right now, the University of Michigan Space Weather Modeling Framework Geospace model of the magnetosphere and the whole atmosphere ionosphere plasma electrodynamics model, or WAM-IPE model that Sue talked about, which is the operational ionosphere, thermosphere, mesosphere model at SWPC, and linking those two models together. Currently, they operate as completely separate models, but there are great benefits, we believe, in linking those two models. It's also worth pointing out, as Sue also mentioned, that the WAM-IPE sits on top of the global forecasting system. So we really, once we do this linkage, we'll have a unified model from sea level all the way out to the edge of the magnetopause and the solar wind interface. And we think by doing that, we'll have a much more accurate, in particular, electrodynamic specification for WAM-IPE in the ionosphere. Okay, so a quick review of the geospace model. Geospace model is really three different models coupled together under the space weather modeling framework. And it's the BATS-RS MHD model, magnetohydrodynamic model of the outer magnetosphere. You can see there the Earth is that little dot in the middle of the blue square. So the BATS-RS model covers the whole magnetosphere, the magnetotail region. Inside of that, they have the Rice convection model, which is modeling the inner magnetosphere, the radiation belts. And inside of that, they have the Ridley ionosphere, polar ionosphere model, which handles the polar energy inputs from the magnetosphere into the ionosphere. So that's the geospace model currently. And you can see field aligned currents, electric field, and plasmas and magnetic fields are going back and forth between these models under the space weather modeling framework. This is again that same slide I showed before, just showing what it outputs, variations of the Earth's magnetic field in the magnetosphere. WAM-IPE, excuse me, WAM-IPE, as Sue told us in detail, is the current operational ionosphere, thermosphere, mesosphere model, which takes input of solar extreme ultraviolet radiation. As something I didn't mention, one of the things that all of the current ITM models, to my knowledge, do, instead of using the actual EUV irradiance that we measure on the GOES satellites, they use a parameterized index called the F10.7 index to capture the variation of extreme ultraviolet input into the upper atmosphere. Now, why do they do that? Excuse me. Never eat peanuts before you have a talk. That's a tip, pro tip. Why do they do that? Because F10.7 is a ground-based measurement for one. It's a radio band measurement, but that radio band, the 10.7 centimeter radio, happens to vary in very close correlation with solar magnetic activity, which therefore varies in very close correlation with extreme ultraviolet irradiance. So it's also a measurement that goes back to 1947. So since 1947, we've been measuring this index called the F10.7 index, which can be used as a proxy for extreme ultraviolet irradiance. So that's why these models tend to use that number rather than the actual measurements we're making in the extreme ultraviolet. But I'll talk about some of our plans to actually incorporate GOES measurements of actual extreme ultraviolet irradiance into WAM-IPE and WACMX as well. And then, as Sue said, the WAM-IPE model also uses real-time solar wind and geomagnetic KP indices as their inputs. And you can see here, it's addressing this sort of 0 to 400 kilometer critical upper atmospheric into low Earth orbit regime. In particular, the space station sits there at about 380 kilometers. So we're capturing a lot of the critical altitudes for low Earth orbit operations with the WAM IPE model. Okay, this is a look at the IPE model. It's an interesting model because it's gridded on, you can see on the right there, the ionosphere is gridded along magnetic field lines. So it's not a pressure grid like the WAM model as shown on the left. And currently the Earth Systems Modeling Framework is used to link these two models together. So WAM and IPE are very different models in how they're gridded. They have different physics, but the ESMF is what we use to communicate between these two very different grids. This is a block diagram of EUV showing that the irradiance again is modeled with the EUVAC model, which is a fairly mature model, let's say, using again this F10.7 proxy and outputting the irradiance physics into the WAM model and also the IPE model. The Weimer model is what's used as that kind of polar ionospheric model. Currently, it's an empirical model. It's not a full physics-based model. It takes solar wind and geomagnetic information into it and outputs polar electric potential for the IPE model. So that's one of the things. Both of those are fairly old models, empirical, and those are two points that we'd like to address with the SWORD Center, improving those parameterizations in both the WAM and the IPE models. I'll skip this slide. This is just another view of the WAM IPE model that you saw in my previous talk and in Suwei's talk. So SWORD will have sort of two tracks of research, and they're color-coded here by school colors. So University of Michigan, and the blue and gold is on the left. They're doing most of the track 1 work to integrate those two operational models, the geospace model and the WAM IPE model. And we're also going to be working with them to integrate the IDEA data assimilation system that Eric Sutton has developed into that coupled model later on, once the two models are coupled. Track 2, which is the blue, the black and gold coloring of CU, is really being led here out of the CU, and that's one of the reasons that this workshop was initiated, is because we are focusing on data assimilation research here at CU. And so when we started working on track 2, I contacted Tom, who I know from my time at NOAA, and I said, hey, we're looking at using JEDI for our data assimilation in track 2 research of SWORD. We should get together and talk about how we might facilitate that. And that led to this workshop. So it's one of the first really positive outcomes of the SWORD system. Both tracks will be unified on AWS cloud-based systems. So we have a very portable and easily validated model system. And then on top of all of this, we're going to have a machine learning effort to develop surrogate models and accelerate data assimilation, as you'll hear a little bit from Enrico, who's leading that effort for SWORD later today. So coupling the models is going to look something like this. Now you can see the geospace model with its existing coupling on the upper level there, but now we have the WAM IPE model in the lower right, and we're going to be feeding more accurate ionospheric conductances, more accurate neutral winds and field-aligned currents back into the RIM model, back therefore into the convection model. And we'll also be getting, hopefully from the Ridley ionosphere, better electric potential and diffuse aurora inputs and discrete auroral inputs than we get currently from the Weimer empirical model. We won't be changing in the first round the inputs to the model, however. So one thing we have done recently is initiated a collaboration with the NCAR Earth Systems Modeling Framework Group. That wasn't in our proposal, but once we started work, it became clear that we needed them to help with the coupling between the geospace model and the WAM model. So they're on board now as a formal partner. In fact, it reminds me I should add their logo to the splash page there. And we're working with them to initiate some work with, for instance, a standalone IPE model that then can run and couple to the SWMF geospace model more accurately. Future plans, we're going to be doing grid remapping between the Ridley ionosphere model and IPE. And we're going to finally replace the standalone or the fake IPE that we're working with the real IPE and perform tests and tune the coupling. So that's work that's ongoing. We hope to have that concluded by the sort of the middle or end of next year. As I mentioned, Eric Sutton has an iterated driver estimation and assimilation model that has been successfully tested on other models like the TIGCM ITM model, and he'll be implementing this model into the coupled WAM IPE as SWORD progresses. Right now, he's working with the standalone IPE model, as you saw in my earlier talk, and that seems to be working fairly well. In track 2, one of the things we want to do that counts as sort of a data assimilation or data integration effort, if you will, is replace that parameterized one number, F10.7, with the actual extreme ultraviolet input or output, I should say, from the sun that we measure now on the GOES EXIS instrument. So there's at least 3 EXIS instruments up there flying now. They measure solar output from the X-rays all the way through to 140 nanometers. We're going to be replacing the EUVAC empirical model then with something called the FISM-OP model, which will take the real-time GOES data and translate it into sort of 37 band passes that can be integrated into ITM models. And this is work that's already been tried out with the WACA model, for instance. So what we'll do is we'll be refining this sort of real-time feed into WACM for testing, and then eventually translate that work into the WAM IPE operational model for final integration. And then the other thing we're looking at, which is directly relevant to this workshop, is assimilating data into both WACMX and WAM IPE as we move along on a research basis on WACMX and a more operational basis with WAM. These various data sources that we have available. As Sue mentioned, we're looking at commercial constellation precision orbit determination data. We're looking at meteor radar networks for mesospheric neutral winds. That's a very interesting global network that exists, and we're hoping to help expand that through the NASA Center of Excellence effort here. There's Fabry-Perot interferometer networks, which also measure neutral winds in the mesosphere, which could be interesting. Sue mentioned Cosmic 2. Of course, we heard from Ricardo about Time Saber as a good source of assimilation for the mesosphere. And then finally, NASA Gold, which we'll hear about later from Fazlou Lasker and Nick Petitella, and using that for temperature integration into the thermosphere. And I believe that's it. So I can take a brief question or two, and then we can move on. Thank you.
Are there any questions for Tom? Stephen?
Just a clarification, really. The intent is not to merge these 3 different models into a single model, but to keep them separate, but connect them through the framework that you're developing.
Yeah, that's correct. It's really that, you know, the geospace model will remain its own integrated 3 model assembly, if you will. WAM IPE will remain its own model, but they will be run in concert using the ESMF intermodal communication framework. Yeah.
Okay.
Right.
Go ahead.
Sorry, one question on your last slide where you had all the different data sources. Is there a plan to assess which one of those observations will have the largest impact on model fidelity?
Yes, and thank you for that question. It's a very good question, and it brings up the issue of OSSIs. As Tom mentioned, that's one of the key enablers that data assimilation will provide, is the ability to simulate the effect on the forecasts if you assimilate a given data set. And as Ricardo showed, they've already done studies between MLS and SABRE. Those are essentially the kind of studies we'll be doing with these various data sets to see where we get the biggest increase in the forecast skill. So OSSIs are a big part of SWORD, or will be. And also creating these reanalysis data sets that Ricardo mentioned, where we can go back and have a historical, say 20 years of WAM IPE runs with data assimilative corrections. So we know it's got the best potential, model of the atmosphere as it was for use in something like machine learning surrogate development. So.
All right, so we need to move to our next speaker. That's Enrico, and we're going to talk about data assimilation and machine learning for space weather.